So, as you all know, because of this video, I am not here. I am on a flight from Copenhagen to Stockholm. So, we are going to do things asynchronously today. So, we are going to learn about a one-way analysis of variance, which is also called an ANOVA. Um, I always thought it sounded kind of astrological, but nope, it's just a way to do statistics. So before I get into what's on the slide, we've learned how to compare means of two groups. Now we're looking at comparing means of three groups or more. And the way we do that is by analyzing the variance between groups. So let's think about what variance is. So variance is the average squared deviation of scores from the mean of the distribution. So here, just to remind you, is the formula for a sample. And when we work with ANOVAs, we are always working with samples. So here, variance is calculated by simply taking the sum of squares and dividing by n minus 1. What we're doing here is really dividing the sum of squared deviations, so variance, or what you would use to calculate the variance, over the degrees of freedom. So remember that variance can't be negative. When we're looking at the difference between something, we can never have a negative number, otherwise they would be overlapping. So our lowest variance possibility is 0. So again, we are just looking at the variance with 0 as the lowest possible value to determine whether there's significant enough variance between the three or more groups to determine them as significantly different from each other. So again, we use ANOVAs when we're comparing more than two groups. The reason why we wouldn't just do multiple t-tests, we already know how to do that, is because we would increase the likelihood of committing extreme type 1 error. Remember that type 1 error is when we say that something is there when it's really not there. Every time we do it, every time we run another t-test, we run that risk. In order to compare three different groups, we would have to run 3 t-tests. We would have to compare group 1 to 2, 1 to 3, and 2 to 3. Anytime we run a statistical test, it increases our likelihood of error. So the name of the game in stats is to do the least possible tests to get the most impact. So again, we're looking for differences in variance across our three groups. So suppose we're concerned with testing the effect of a new drug on depression. We would want to know how different the scores are between the groups, how different the scores are within the groups, and which differences are most likely to support that there's an effect of a new drug. So when we talk about differences in scores between the groups, we want to see whether the drug is significantly different than the placebo condition, the drug is significantly different than the waitlist condition, or the placebo, how different that is from the waitlist condition. When we think about variance between groups, that means I might want to know how different each of these scores are within the drug group. Placebo, how different these scores are within the placebo group, etc. And then that last question, what differences are most likely to support there's an effect of a new drug? So if we're testing the effect of a drug, we would want this group to be meaningfully different than this group or that group. If this group is not different than the placebo, we can't say that there's an effect of the new drug. So when you talk about variance, and when we set up ANOVA experiments, we have two things that we think about. We think about factors and we think about levels. So factors are essentially what it is we're actually testing. So here, the factor is treatment. Are you getting a drug as a treatment? Are you getting a placebo as a treatment? Are you getting nothing as a treatment? When we think about levels, that just refers to the different conditions. So the 3 different groups. So drug, placebo, waitlist. Maybe an easier example to think about is coffee versus or across lab section groups. So here we have one factor, which is coffee. Groups can either have coffee or no coffee. And we have 4 levels, so 4 lab sections. So we are looking for a ratio of differences across and between our groups, or excuse me, within and between our groups. And this ratio is known as Fisher's F. So when you calculate an ANOVA, you are calculating an F ratio. So the differences between groups can reliably be attributed to the independent variable or the factor, so whether groups have coffee or no coffee, for example. But differences within the group can only be attributed to individual differences, and those are unexplained variance or experimental error. So whenever we have something that's unexplained, it's called error. And this makes sense, right? If we are controlling a factor and we are looking at groups compared on that factor, when we change that factor and it leads to a change in the groups, it makes sense that we can attribute it to that factor. But if I see differences within my group, for example, within my lab section 3, this could be a whole host of things. It could be who showed up that day. It could be if they had caffeine already. It could be if they got little sleep, if they're really stressed. So many different things could be attributed to the variance that happens within those groups that I don't have control over. So again, that is called error or unexplained variance. So in order for there to be a reliable effect of group, we need the difference between the groups, or the variance difference between the groups, to be larger than with the within group difference. So when we look at Fisher's F, we can calculate the Fisher's omnibus. So that's the same thing. It just means the variance between over the variance above. You'll also see this MS, mean squares between, mean squares within. It's the same thing. So when you see MS, it's equal to variance. And again, we're just dividing between group variance by within group variance, which means explained variance over unexplained variance. And that gives you the effect of the independent variable over the error. But so you know, this is going to be your formula for calculating a Fisher's F. So let's talk about sum of squares and degrees of freedom. So we know that variance is the sum of square deviations over our degrees of freedom, but we want to think about how many measurements are free to vary. So you always want to think back to n minus 1, which is the case for each group. Between groups, we want to consider how many groups are free to vary. So that's going to be your number of groups minus 1. So in the coffee example I just showed you, where there were 4 groups, our between groups df is going to be 4 minus 1, which is 3. Then we get to our within groups degrees of freedom. And that is when we ask ourselves how many people are free to vary per group. So that's when we add up all of the people and subtract 1 per group. So that's going to be all of the people minus the number of groups. So let's say we had 20 people in each group. That means we have 80 people total, minus 4 groups. So that means our within groups df is going to be 76. And just a note here that the big N refers to the number of scores in the entire sample, where the small n refers to the number of scores in each group. So when we state our hypotheses for ANOVAs, we need to know that the ANOVA only examines whether there's a difference between groups. It doesn't make specific directional hypotheses, and it doesn't identify the specific differences. So when I do an ANOVA, I'm not learning whether there's a specific difference between group 1 and group 3. My ANOVA just tells me whether overall there's a difference somewhere among these 3 groups. In order to find where that difference is, we do something else, which I'll explain later on. So that means that the null hypothesis for ANOVAs is that the means are not different from each other. And the research or alternative hypothesis is that the mean of at least one group is different from the mean of at least another group. So under the null, the most likely outcome of F is 1, which means there is no difference between or within the group variance. That means that our fraction would be 1 over 1. Now, when we find our degrees of freedom here, we are going to be looking at a new table. So now we have our F table. It's a little bit hard to see. When we calculate our critical values, we need two pieces, or actually three pieces of information. We want to know our alpha level, whether it's 0.05 or 0.01, and we want to know our between groups DF and our within groups DF. So for example, or actually before I get into that, I want to mention that our between groups DF is our numerator, so the number that you do first, and our within groups DF is our denominator, so the number you do second. So for example, let's say we have 3 groups for a total of 30 people. So our between groups DF is the number of groups minus 1, so that's going to be 2. So I'm going to go over to this column. And our within groups DF is going to be the total number of people minus the number of groups. So 30 minus 3 groups is 27. So that takes me over here. So this table is a little bit wonky because it gives you 0.01 and 0.05 in each sort of cell. So you need to make sure that you're looking at the right number. At the top of the table, it says that 0.05 is Roman type and 0.01 is boldfaced. So depending on what alpha level you're given, it's going to be one of these two numbers. Okay, so here are our steps for the ANOVA. There are a couple of new steps in here, but you're going to see that it looks a lot like our t-tests. So the first thing that you're going to do is make an SS table for each group. You're going to find the variance for each group, which is just your sum of squares over your DF for each sample. So again, this is just like what you did before. Then you'll calculate your variance within, or your MS within. Remember, they're the same thing. In order to do that, you'll add up the variance for each group and divide it by the number of groups. So that's kind of part 1. You can think about that as part 1 of the steps for an ANOVA. The next thing you'll do is you'll find the grand mean. So the grand mean is found by calculating the total of the means across your 3 groups. So your mean for sample 1 plus mean for sample 2 plus mean for sample 3, and divide it by the number of groups. The next step is to find the DF between. And we know that to do that, we just take the number of groups minus 1. So that's sort of part 2, finding the grand mean and the DF between. Now you'll want to find the variance of the distribution of means. For this, you have to make a second table, but it's much smaller than the first tables that you were making in step 1. So here, you're going to make a second table with 3 columns. You're going to line up your sample means, and your deviation from your grand mean, and your squared deviation from your grand mean. So essentially what you're doing is making a sum of squares table for just your sample means. From there, you're going to calculate your variance of distribution of means. So what you're going to do is find that sum of all of those deviations, so just your sum of squares, and divide it by your DF between. So essentially, again, just to recap, you're making another sum of squares table with your sample means, and then dividing that number by your DF between. After that, you're going to find your variance between, or your MS between, And all you're going to do is multiply the number you got in step 2 by little n. So little n is the number of participants in each sample. Then you'll find your F ratio because you have your variance between and you have your variance within. So you'll just divide between over within. Make sure to not mix that up. After that, you'll find your critical value. Remember that you need to know both of your DFs and your alpha. And then finally, you'll compare your F value to your critical value and you'll make a decision. So let's walk through an example. A team of pharmacologists wanted to test if a new SSRI can cause a different effect in the experience of depression. 15 clients were given different drug treatments 6 weeks before taking a depression index. So scores range from 0 of not symptomatic to 10, which is highly symptomatic. Clients were evenly split so that some took the new SSRI, some took a placebo, and some were placed on a waiting list, so they had no treatment. Below are the depression scores after 6 weeks. Researchers want to be highly confident of the effectiveness of the new drug. Test their hypothesis that the treatment group will lead to different levels of depression. So alpha equals 0.01. So here are our 3 different groups, our SSRI, our placebo, and our waitlist, and I've provided the means